All right, we are now recording. We'll go from the current slide, but before we hit that, let me hit the other announcements. You know the first two. If you're interested in the math team, Mr. Rossi is meeting tomorrow and every Friday. Well, not next Friday, but most Fridays at 12 o'clock noon in on the Birmingham West Campus, the Science Building, which is the C Hall, and C100. Right next to the building where the library is. The D building is the library. And then they meet again on Mondays, not this coming Monday, but on Mondays at 3, same place. And I have a student in my Monday, Wednesday morning class. He's been going to it. He said it's been a lot of fun. Believe it or not, a lot of fun. And I can tell a huge difference in his participation in class. First of the term, he was so hesitant, uncertain, and stuff like this. Now he's on top of everything. He's learning math really, really well. So, Brianna's here. Good deal. And if she wants a button, there's buttons here. March for our lives. It's this Saturday, 2 o'clock, Railroad Park. Have as many as you want. If you have more people, you might like to go. All right, and then this is the important announcement I wanted to make sure gets on Screencast-O-Matic on YouTube so everybody hears it. You'll probably see signs about this, and this is informational sessions on institutional scholarships. I'll explain that in just a second, and summer Pell scholarships. This will be Wednesday when we get back from spring break, April the 4th, Wednesday, 11 to 1, and again 5 to 6:30 here on this campus, Vassar campus, in the faculty staff dining hall. Now, I don't know if y'all know where that is. If you know where the cafeteria is, it's just next to the cafeteria. Okay? If you go down, any way you want to get there, go down to, and here's listed right here, faculty staff dining, right there, okay? You can go down this long hall, take the first stairwell, go down. Easier to go to the second stairwell, go down. Feel a little bit of crisscrossing around. Go toward the cafeteria, which is right here. You'll see it on the left. If you go down this corridor that goes over to financial services, swing on around through the bookstore, and then when you're heading up to the cafeteria, it's on the left, okay? So that would be where it is, both times, 11 to 1, and 5 to 6:30. Now, it'll also be on the Birmingham campus if you're there, okay? And this will be at the Leon Kennedy Center in the cafeteria. The faculty staff dining room here on this campus, cafeteria on the Birmingham campus. Sponsored by Office of Student Financial Services. That's Wednesday, April 4th. Now, let me explain a little bit. A lot of students who are on Pell Grant, if you're full-time, most of the time the Pell Grant runs out by the end of the spring, right? Okay. So if you weren't quite full-time and have some Pell left over, you can still use it in the summertime, okay? But if you don't, we have some institutional scholarship money, Lawson State money that they do. It may only pay for one course. I guess they might even pay for part of a course, but you may not get a full load on it, but you can get some assistance in the summertime. Yes?
If you do your FAFSA for 2018 and 2019,
Okay, say that a little louder.
if you do your FAFSA for 2018 and 2019, it'll go to your summertime.
They will. They changed that back?
Change it this year.
Wow. Okay, they did this several years ago, and it was a roaring success, and then they changed it back. So if you do your FAFSA now, and this is what these sessions are about, if you do your FAFSA now, that's what you're saying, and you get it in time for summer, you can use it for summer term. Fantastic. It was a great program that we had, like I said, several years ago. I would say probably close to 8 years ago, and it worked so well. I mean, we had record attendance in summertime, and then after a year or two, they stopped because it was costing too much or something. I don't know what the reason was. But anyway, I'm so glad to hear it's back. Now, any of you who don't qualify for FAFSA, then you can use those institutional scholarships. This opens up more money for you because we got the money set aside, not a lot, but some. And sometimes it may only do one course or maybe even just a partial, but you can get some money, institutional money. Okay? Now, I marked those people who were here earlier. Let me add this. Gavin's not here. Monica's not here. CJ's not here. Kelsey's not here. Jasmine Fowler's not here. Kiara's not here. Thomas not here. Tanisha not here. Tadarius not here. Chris is here. Okay. All right. Taylor's not here yet. Kayla is not here yet. Jacoria not here yet. Melvin's not here. Kaylee is here. Okay. Amber not here yet. Ioana's not here yet. Lindsay is here. Stephanie's not here yet. Fred's not here yet. And Jayla's not here yet. All right. Anyone whose name I missed, except those I called earlier, 1, 2, 3, 4, 5, 6, 7, 8. 2, 4, 6, 8. Who do we appreciate? Okay. I heard no answers. Okay, never mind. All right. Now, for those who see some people wearing badges, I do have buttons. This coming Saturday at Railroad Park, 2 o'clock, high school students from across the area have organized to have a March for Our Lives in commemoration of the students who got shot. There's a big march going on in Washington, D.C., but local marches in various cities, and this is for in general, students who have been killed, okay? It was prompted by the Parkland. We've had a Huffman student shot. We've had a nurse supervisor over at Highlands UAB. There will be people there commemorating all those, and if you know of anyone who has been the victim of gun violence, encourage anyone to go and participate in the march. Wear the colors that was either that person's favorite colors or your school colors or whatever, because that's what it's all about. And it's done by high school students. I met with them on Sunday, and they are really on the ball. Okay. Any questions, math or otherwise? All right. Where we were last time, we are looking at higher order algebraic equations, okay? And with the higher order equations, they're not nearly as easy to do as the quadratics. Quadratic, get it done. I mean, parabolas, you know what they look like. These higher order, higher degree equations, not quite as easy. So, we talked about, what's the first thing we talked about with these? What can you determine just looking at the equation? Say again? Well, okay, that's what this is going to be talking about. What I was hinting at is your end behavior. Just looking at these polynomial functions, what term is it that gives you most of the information you need about where the function's going in the long run? The leading term, okay? It tells you when x gets very, very small negatively, very large negatively, then which way is it going? It's either going to positive infinity or negative infinity. When it's going very large, x is getting very large positively, the function's going very large positive or negative, okay? And that leading term tells you which way it's going. Two things about the leading terms. What? The degree of the leading term. If it's an even degree, it's going like this. Either up and up or down and down, going in the same direction. Odd function, odd degree for the leading term, is going in opposite directions. But we just don't know which. What tells you which direction? Okay, that's the exponent. That's the degree. What about the leading term? Okay, that's the exponent. Okay. Positive or negative, whether the coefficient for the leading term is positive or negative. If that's an even exponent, positive, it's going up and up. Guaranteed. If it's even exponent for the leading term, but negative, it's going down and down. No doubt about it. If it's an odd exponent and it's a positive coefficient, it's going exactly the way you wrote. Negative's going negative, positive's going positive. Okay? And if it's a negative coefficient but odd exponent, it just reverses itself. Negative goes positive and a positive goes negative. Okay? We talked about that last time and rapidly forgot. Anyway. So, what happens in between? Well, the best guess is what you are suggesting here. Where does this function cross the x-axis? That's going to be the zeros for the function, right? That's where y is equal to 0, and f of x is y. So when y is equal to 0, f of x is 0, that's going to give you the zeros of the polynomial function. Strong interplay between the graphical and algebraic approaches to this problem. So even if you don't draw the graph, think the graph, okay? Or thousands of words pictured, right? When f is a polynomial function, that's all we're dealing with in this chapter so far. We'll do rational functions later. And a is a real number, okay? Some real numbers. Pretty vague there, right? The following statements are equivalent, okay? Now let's just say somehow, some way, we knew that x equal a is a 0 of that function. X equal a, whatever a is, maybe right there, and that's a 0. I don't know who left this here. I'm sure it was me. Okay? So, if a is here, or here, if that's a 0 of the function, x equal a is a 0 of that function, then the following three are also true. That x equal a is a solution for that polynomial equation, f of x equals 0. Because what is it? If that's on the x-axis, it's a 0 for the function, then f of x is not equal to 0. So this a would be a solution. It will also be a 0. But not just that. X minus a is going to be a factor of this f of x. It will be a factor. Now, how do we know that? Well, if x is equal to a, where did that come from? Subtract a from both sides, you get x minus a is equal to 0. Hey, that's how we found out that was a 0 in the first place, right? So x minus a is going to be a factor of the polynomial function. And the last one, and I think I would have said this up here, a0 is an x-intercept. Because if x equal a is a solution, is a, what do we call the first thing? A 0, a solution, it's on the x-axis, right? So therefore, a0 is going to be one of your x-intercepts. Okay? Got to be. Now, what's more, if this is true, the other three are true. If that is true, the other three are true. If this is true. So if you can find any one of these things, you know the others are going to be true. So these are your conditions that are common to all zeros of a polynomial function. The question is, how do we find it? Okay? We'll hit to that. Let's do example 3 and see what we might do. Here's f of x is equal to negative 2x to the fourth plus 2x squared. And it says find the real zeros. Where would you start? Okay? It's certainly going to be something to do, but what does it mean to be a 0 of the function? A little louder. Set it equal to 0, because f of x has got to be equal to 0. So there's our first step. So let me get my pen changed. That's the first step. Okay. Set that. It didn't change. Yuck. What a pain in the neck this can be sometimes. Okay. Set it equal to 0. Now, who are you? Okay. This guy then. Okay. All right. We finally got two people in the class who are adjacent in the role. All right. It was just aces and spaces here. Okay. So the first thing we do is set it equal to 0. Now we do what Kedrick was suggesting. What's that? Okay. It's what? Okay. Okay, I thought you were suggesting it. Not quite. I thought you were saying, because these are not like terms, but they do have common. Oh my, here's the whole world's coming now. Okay. Okay. Monica's here. Now we got 3 in a row, actually 4 now. And we have Melba. We have another 2 down there. Okay, good deal. Anyone else come in since I called on? Okay. Now, once you've got that equals 0 there, that should send off bells and whistles saying, hey, I think I know what to do here. What do you do? What is one of your first steps if you have a situation like that? What's the F word? Second?
F word?
Yes. Factor! That's what I thought you were going to say before when you were saying common. Factor out. Common factor. Excellent. Excellent. And what is your common factor between those two terms? Okay, a little bit more than that. Okay, I would do a negative 2. X squared. Excellent. X squared. Excellent. Okay. What's left in the first term? X squared. What's left in the next term? No, you factor it out. Say again? I couldn't hear. I heard someone say something. You've already factored out the x squared. You already factored out both of the x's. You factored out the 2. There's a 1. I need something between that and the 1. Huh? You factored out a minus, leaving you... Oh, yes, a minus 1. I feel like a dentist pulling teeth here. Okay. So, there we have factored at least the first step, least common factors, right? Does everybody see where that happened, how it happened? Make sense? Okay. Agreed. Are we through factoring? No. There's something else you can factor. Because this is going to be a minus 2x squared. You're done with that one. How about that next one? Say again? X times x. I'll agree with that. Plus 1 and minus 1. Perfect. Difference of 2 perfect squares always factors to be the sum times the difference of their square roots. Absolutely. In fact, we're going to hit this later. I'm going to tell you now. These are called, I don't know if you remember this from other contexts, these are called conjugates of each other. The first term's the same, the second term's the same except for the sign. Those are called conjugates. Okay? Almost the same, the only thing that differs is the sign of the last term. And those are conjugates. We use them when we're rationalizing irrational denominators, rationalizing denominators. We use them when we're dealing with complex numbers. When you rationalize it, and when you're uncomplicating the denominator, we use them lots of times. In calculus, you'll still be using conjugates of each other. Okay? And we've been using them, we just never called them that. Or not much, anyway. Now, what does this tell you? Here we have 3 factors. Actually, you could say you have more, like a negative 2 times an x times an x. You could say that if you wanted to. Do you want to? Huh? You don't? Okay. So let's just take it as 3 factors. And the product of the 3 is equal to 0. What does that tell you? How can you multiply 3 numbers together and get 0 as a result? What has to be true? One of those has to be 0, at least one. So we say then either negative 2x squared is equal to 0. That would make the whole thing equal 0, right? Get out of there. Okay? Or, next, x plus 1 equals 0. That would make the whole thing 0, right? Or, x minus 1 equals 0. Guess what? We're going to come up with 3 zeros to this polynomial function. Now, time out a minute. I forgot this too. What do we know about the end behavior of this? We're not going to graph it necessarily. Oh, yes, we are. Yeah, yeah. So, what do we know about the end behavior of that? It's what? Really? Okay. Leading coefficient is negative, and the exponent is even. So the even exponent says they're going the same direction. The negative coefficient means they're both going down. So we know they're going down in both directions. Okay? Now, another thing we learned, I forgot we had this one. At most, how many zeros does this have? 4. Up to 4. May not have 4, but it has up to 4. Here it looks like we're going to come up with 3. Fine. Next thing we're going to ask for, how many maximum turning points could you have? 3. One less than this n. Okay? Again, that leading term tells you tons of information. Okay? So what are our 3 potential zeros here? A little louder? Okay, equals 0. So how would you solve that for x? It's pretty easy. How's the only way that negative 2x squared could be 0? Yeah, x has to equal 0, right? No way around it. Okay? For x squared to be, well, you can divide the negative 2 into both sides, and therefore you have x squared is equal to 0 over negative 2, which is 0. Okay? And how the only way x squared can be 0? X equals 0, x equals 0. That's all. Okay. How about the next one? A little louder? Okay, this one would be, because here you add 1 to both sides, that gives you x equal 1. Negative 1, because if you subtract 1 from both sides, you get x equal negative 1. Yeah. There are 3 zeros. Absolute. Okay? Not possible. Those are the 3 zeros. Now, I do want to say this. Okay? This is called a double zero. Because you could have x equals 0 and x equals 0. I don't know if you ever saw, you probably aren't interested in these kinds of shows, but the old comedy show with Bob Newhart, he was in several of them, but they're living somewhere out in the countryside or something like this. He had this neighbor, and he came up and said, I'm thus and so, this is my brother, Daryl, and this is my other brother, Daryl. Okay? They never said a word, but it always came in 3, and only one talked. And this is my brother Daryl, and my other brother Daryl. Well, it's the same thing here. This is a 0, 0, and this is the other 0, 0. Okay, that's a double zero. Okay, and we're going to see a ramification of that just a little bit later, hopefully today. We'll see what happens when you have a double zero. That's called the multiplicity of 2. Yes.
So if you would have factored that 2x squared, it wouldn't have been a double zero.
Well, no, that's exactly what you do. If you factor this, it's negative 2 times x times x, okay? Now, negative 2 is never equal to 0, right? Can't be. It's negative 2, not 0. But the only way this can be 0 is if x is equal to 0 or x is equal to 0. Yeah, that makes it a double zero, okay? Each of those x's would have to be 0 because they're the same, okay? And the only way you can multiply these two together to get 0, even with negative 2 in there, one of those has to be 0, and if one's 0, the other's 0 as well. All right. And Jayla's here. All right. All right. So, we've done the first part. Find all the real zeros of this polynomial equation. Then determine the maximum, we already did this. The maximum number of turning points. What do you think? The maximum number would be 3. This one may not have 3, but I think it probably does. You want to go on and give a shot at the graph? Or not? Let's see if they do in the book. Yes, they do, and they'll show it. You want to do it and just wait and show it? Okay. So let's Erase all this ink. You got it? Okay. Now, to solve, find all the real zeros, we set f of x equal to 0. So instead of f of x equal that, we set that equal 0. Those are going to be the places where it crosses the x-axis, the zeros of the function. And the next thing they do, remove common monomial factors. So they factors, same thing we did. And here's a hint, folks. When your leading term has a minus in it, and you can factor it out, get rid of it. I mean, factor it out of there, okay? And that's why we pulled the minus out too. And you see that left us something that was factorable. The other would have been 2, but it would have been harder to see, okay? So that's exactly like we did. But then we noticed that the second factor is still factorable. So factor it again. And there we have exactly what we had, negative 2x squared times x minus 1 times x plus 1. They did the order differently, but same thing, is equal to 0. Now that we factored it completely, now we set each factor equal to 0. Okay? So the real zeros are x equals 0. You could say, or x equals 0. Okay, you're just repeating yourself. X equal plus 1 from the x minus 1 factor, and x equal minus 1 from the x plus 1 factor. Remember our 4 conditions? If this is a factor, there's a 0. If that's a factor, that's a 0. You know, if x minus a is a factor, x equals a is a 0. And vice versa. So that's the same thing we were talking about before. Okay? Now, because the function is a 4th degree polynomial, the graph of the function can have at most 4 minus 1 or 3 turning points. Let's see if it does. Ha! Here we go. X equals negative 1 is 0, so we know negative 1, 0 is what? What do we call this? Has a special name. Okay, think of the defensive backs for Alabama or Auburn or wherever in Alabama. We'll stick with Alabama. What last year, not this past year, but the year before, what did they lead the nation in? Interceptions. So this is a x-intercept. This is where it's intercepting the x-axis, right? Cross the front and got the ball, right? Got the ball. So that's the negative 1, 0 is an x-intercept. X equal negative 1 is a 0, and x plus 1 is a factor. All those things are true, okay? And x equal negative 1 is a solution for this thing equal 0. Same thing. Here's our 0, 0. When you plug in a 0 here, well, we found that x equals 0 was a 0, therefore the y is 0. Now, here's the difference. Notice this was a single 0, x equal negative 1. There was a single 0, x equal negative 1. This was a double 0, x squared equal 0. Guess what? It comes down and touches, but doesn't cross. Single zeros cross, multiple or double zeros kiss the axis and go back the same way. They don't cross it. Okay? We'll come into that a little bit later and we'll expand it to higher orders. But that's what we've got now. So 3 zeros and how many turning points? 3 turning points. 1 here, 1 there, 1 there. So yeah, you didn't have the maximum number of zeros unless you count the 0 twice. Okay? X equals 0 and my other brother x equals 0. A double 0 there, single 0 at the other. Make sense? Oh! And look at the end behavior. Going down and down, just like we knew it would have to. Right? All right. Enough on example 3? Ready? Okay. Now, in example 3, this is what I was just telling you. Note that because the exponent is greater than 1, this factor, negative 2x squared, yields a repeated 0. I called it a double 0 because the exponent was 2. It's called a repeated 0 at x equals 0. In general, anytime you have a factor, x minus a, raised to the kth power, this one happened to be x minus 0 raised to the kth power. We just said x 2. The k was 2 there. Where k is greater than 1, that yields a repeated 0 at x equals a. Now we also say that has a multiplicity of whatever the k was. So this multiplicity was 2, right? Okay. When that k is odd, the graph crosses the x-axis at x equals a. When that k is even, it touches the x-axis but does not cross. I like to say it kisses the x-axis and goes back the same way. Okay? Kiss and run, you know. All right. Not a bad idea. No, okay. Now, I don't know why they say k has to be greater than 1. Guess what? That works with k equal 1 too. Okay? It's just now a multiplicity of 1, meaning it only has 1 0 there, and 1 is odd, and it crosses, okay? So it still holds true for 1. It's just not repeated. It's just 1. Ah, someone snuck in on me. Okay, trying to sneak in under the wire. CJ's here. Boy, the top part of the alphabet is doing quite well now. 5 in a row. Okay? Okay. Yeah. Okay. Yes. To Darius, I knew that. I was just so hoping we would have. Now we got 2 in a row down there. CJ's not here. Okay. Sorry. Okay. So we got 4 in a row at the top. Okay. But 2 in a row in the middle now, which is Darius. Okay. So any questions about repeated zeros, multiplicity? You understand what we mean by it? Okay, good deal. I have a feeling you may see this somewhere later. Okay, just a gut feeling. Okay. To graph polynomial functions, that's what we're all about here, right? This book loves graphing. Use the fact that the polynomial function can change signs only at its zeros. That's the only place it can change signs. If the f value is positive, and then it becomes negative, there has to be a 0 in between there. Because polynomial functions have 2 characteristics. Do you remember what they were? Smooth and continuous. So they can't jump over the x-axis. That wouldn't be continuous. So if it's positive here and negative there, it's got to cross the x-axis at least once in between. If it's negative here, positive there, it's got to cross the x-axis somewhere in between. Okay? So, between 2 consecutive zeros, a polynomial must be either totally positive or totally negative. Otherwise, it would have to cross. And we said these are consecutive zeros. So it can't have any more zeros in between if those are consecutive. So that leads us to, well, more talking, okay? This means that when you put the real zeros of a polynomial function in order, you just found them by factoring or however, we're going to learn some other techniques later. They divide the real number line, in other words, the x-axis, into a bunch of intervals in which the function has no sign change. So if you have a 0, say, here and there, there and there, there and there, that's a lot of zeros, okay? Between these two, it's either going to be totally positive or totally negative. It can't change sign because you'd have to have a 0 if you did. And you said those are the 2 consecutive zeros. Okay? Now, do they have to change signs between them? No, because you could have an even multiplicity there, and it'd be positive here and positive there. That would be okay. But it can't change signs in between the 2 zeros. Okay? That's what this is saying. These resulting intervals are called test intervals. Once you get those zeros there, and this is for later when we're doing this, maybe real soon, what we'll do, we know where the zeros are, but we don't know what the function is doing in between the zeros. So what do? We pick a point, not a 0, but something in between the 2 zeros, pick a point for x, plug it into the function. If it comes out positive, we know it's going up. If it comes out negative, we know it's going down. And it's going to be negative or positive everywhere between those 2 zeros. Okay? That's what we call them test intervals. Pick a point there, test, and see what it is. Choose a representative x value in that test interval to determine whether the value of the polynomial function is positive, lying above the x-axis, or negative, lying below the x-axis. All right, now that leads to what I thought was going to be the next slide before, the intermediate value theorem. I'm afraid, yeah, they skipped 2 examples here. So before we get intermediate value theorem, let's go back and do example 4. Okay. Oh, here we go, sketching graphs. Does that sound like fun? Okay. I should hear a big resounding yes. Well, I didn't hear it. Okay. Sketch the graph of f of x is equal to 3x to the 4th minus 4x cubed. Okay. Now, before we sketch the graph, in fact, I'll go on and start the sketch of it. Okay. I'm going to cheat a little bit. Okay. I'm going to put my x-axis down there. Anyone think of a reason why I did that? Well, it may. I guarantee it won't. I'm thinking it will. But where's it going to be in the long run, Long Lewis? It's going up and up because you have your end behavior. Even exponent of your leading term, meaning it's going in the same direction, positive coefficient is on the up and up, right? So we know that right off the top. It's going positive here and positive there. That's why I put the axis down there, because I figure most of the action is going to be above the x-axis. I may be wrong. Well, I know I'm not wrong in the long run, but in the short run, I think I'll be okay. Okay? Now, so we've done the end behavior. Next, what would we do? Find the zeros. How do you do that? Set it equal to 0. Good idea. And then what? Factor. And what can you factor here? Help me. A little louder. I heard an x. I heard an x squared. Is that the best we can do? X cubed. Factor out x cubed. And what do you have left in the first term? 3x. And then the second term? A little louder? -4. Perfect. Okay? And that's equal to 0. Right? Now what does that tell you? It says what? Okay, can you factor any more? Wish we could, but we can't. Unless you do the x, you do x times x times x. You could do that, but that's not going to tell you anything new. So what do we do from here? Once you get the products equal to 0, second, set each equals to 0. So this tells you that either x cubed is equal to 0 or 3x minus 4 is equal to 0. Okay, x cubed equals 0. What does that tell you? X equals 0. Okay? Absolutely. The only way that x times x and x can be 0 is if x is equal to 0, right? If x is anything else, it's not going to be 0. Okay? This over here, what would we do? Not yet. Add 4 to both sides. And then you get 3x is equal to 4, because that adds a 0. And then you divide by 3. Now, you could have done it the way you said, but it would have been fractions a little harder, but I don't like fractions that much. But you could have done that, okay? So this gives you x equal 4/3. That's a 0, okay? So let's start at least drawing our function, okay? There's 0, 0. Let's do 1, 2, 3, 4, 5. -1, 2, 3, 4, 5. Positive 1, 2, 3, 4, 5, 6, 7. Why did 6 not show up? Okay. -1, 2. Okay. Now, where's x equals 0? At the origin. So there's a 0 right there. 0, 0. Now, let me ask you a question. I never ask you questions. Okay, what kind of zero is this? Say again?
Double.
Not double. Triple zero. Okay? A zero of multiplicity 3. What does that tell you about what it's going to do there? If it's even multiplicity, it kisses and runs. If it's odd multiplicity, it crosses. Okay? So what's that going to do? Cross. Now, because it's multiplicity of 3, it's going to sort of act like the cubic function and hang around there a little while, because it's got to get 3 kisses in it, and then it's going to cross. Okay? So it's going to be a little bit of a wobble there. If it's just multiplicity of 1, it just crosses. One way or another. Multiplicity of 2 kisses and runs, and multiplicity of 3 hangs around there a little while, but does cross. 4 kisses and hangs, and then runs back the other way. Okay, so the evens go back whichever way they're going, they came from. The odds cross. The bigger the multiplicity, the longer they hang around there, but they still either cross or run. Okay? And what does the other zero tell us? Where is 4/3? It's at 1 1/3, isn't it? So this is another zero. 4/3, 0. Because remember, your zeros tell you where your x-intercepts are. That's an x-intercept right there, 4/3, 0. Okay? Now, basically, we have enough to graph the function right now. Okay? I know what the book's going to do. The book's going to have you do some test points in the interval. Notice these 2 zeros, because this is a triple zero. You can't do anything in between that. These 2 zeros, they're going to have you test a point out here, maybe -1. Test a point in between the 2, that would be, what's a good point? 1. And test something on the outside, what would be a good point? 2, yeah. Those would be the easiest ones to do. Those would be your test points. Okay? Really, we don't need to. Because we know the end behavior has got to be coming down here. Got to be coming down here to hit this first zero. Because the end behavior is up, right? So to hit the first zero, it's got to be coming down. Now we know it's a triple zero, so that's going to hang around there a little bit, but it's got to cross. Because that's an odd multiplicity. So it's going to cross here, and then it's got to turn back and cross, because that's a single multiplicity, the word multiplicity. It's going to just go right past it. No lingering or anything. Go right past it, and then the end behavior is on. It can't come back again. There's no more zeros. So we know what it's going to do. Come down here, wiggle a little bit, go down, come back up, and head out. End behavior tells us this. We really don't need the test points. Except to tell you how far it's going. So let's use them. Let's do x equal what you want this one to be, -1. So go to the original function. Sometimes it might be better to go to the factored form, but we'll go to the original function. And let's put in a -1. So f of -1 is going to be, get out of there. How do I do that? 3 times, get out of there. Wait, I've got to find my, where did my, oh, there it goes. Okay, say again. Not factoring, we're plugging in. Yeah. -1 to the 4th power minus 4 times -1 to the 3rd. Okay, let's do the math. Let's first do the exponents. 3 times, what's -1 to the 4th power? +1, absolutely. Minus 4 times, what's -1 to the 3rd power? That's a -1, okay? And 3 times 1 is 3. And minus 4 times -1 is +4. 3 plus 4 is 7. 1, 2, 3, 4, 5, 6, 7. Oh, we barely got it in there. There's our x our point at negative 1, 7. So sure enough, it's on its up and up here. It's going up. Never going to turn around and come back. It's on its way out of here. Okay, we know down here, you approach the 0. Because it's a multiplicity of 3, you're going to hang around a little while, but then you got to cross. So let's go to f equal 1. X equal 1. And what is f of 1 then? 3 times 1 to the 4th minus 4 times 1 to the 3rd, and that's going to be, anyone do that just looking at it? Okay, let's do it then. Negative 1, perfect. Hey, guess what? Time out. Whenever you plug in a 1 here, for x, that's always going to be 1, that's always going to be 1. So just add the exponents. It's so easy to do x equal 1. Easier to do x equal 0. I like that one. But this is x equal 1, and sure enough, that's going to be 3 minus 4. So, down here, where did we say it was? At 1, it's going to be minus 1. And we know here it's going to be a 0, because that was our 0. The last test point is 2. F of 2 would be 3 times 2 to the 4th power minus 4 times 2 cubed, right? Got it? Okay, so that would be, I'm going to come down here, 3 times, what is 2 to the 4th? 16, perfect. Minus 4 times, what's 2 cubed? 8, okay. And what's 3 times 16? 48, maybe. Would that work? Minus 4 times 8 is 32. What's that equal to? 16. And guess what? That's way off scale. So it is coming up here. I can't remember why. Let me take a look at this. They say it turns there. I'm not sure it does, but anyway. Oh, let's see. Maybe they don't. Nah. We know it turns somewhere down there, crosses and heads up. Well, doesn't head back, but it heads up really, really fast. It goes to 16 before you get x equal 2. So that's way up there, way past it. Right. Make sense? And that's pretty much what I told you it was going to do. Now, what was the maximum number of turning points we were expecting from this baby? Maximum number of zeros was 4. We only had 2. Maximum number of turning points was 3. We only had 1. That almost was a turning point, but wasn't. Okay? So you don't have to reach the maximum. You just can't exceed the maximum. All right, and that's the picture the book has. All right, that was example 4. You ready for 5? I didn't hear a no, did I? Oh, okay, good. Okay. All right. Can I erase this now? Okay. All right, example 5. Sketch the graph of f of x. I love this one already, don't you? Negative 9/2. Yes, that's so much fun. X plus 6x squared minus 2x cubed. Okay. Says sketch the graph. So I'll go on and do this. And I'm going to put the x-axis pretty near the middle. Okay? Now, before we sketch anything, what can we look at and sort of make a guess on? The what? Okay, we could do that. How many turns maximum could we have? 2. Yeah, 3 minus 1 is 2. Okay, anything else you want to guess at? Okay. Okay, yeah, okay, he's already talking about in behavior, going in opposite directions. And which way would those be going? When you go very negative with x, which way is the y going? Up, you're right. So on this side, it's going up, and on this side, it's going down. You get that from your leading term test. It's an odd exponent, meaning it's going in opposite directions, but a negative coefficient. That means when you go negative on x, you go positive on y, positive on x, you go negative on y. Okay? So we know the end behavior right now. We know the maximum number of turns. What should we do now? Okay, that one looks, yeah, certainly it can be factored. Okay? Now, before you factor, though, because you don't usually factor functions, you factor equations. Does that sort of make a difference? Okay, so what do you want to set this equal to? You're looking for the zeros of the function. So set it equal to 0 first. Now, once you set that equal to 0, that's an equation. Now you can use all the rules for equations that you want to. Remember, you can add the same thing to both sides. You can subtract the same thing from both sides. You can multiply the same thing from both sides, as long as you don't multiply by 0. That wipes out all meaning of your equation, so don't do that. And you can divide both sides by the same thing, as long as you don't divide by 0, because you can never do that. So, does anything strike you as something you might want to do in that equation? Anything you don't particularly like about it? I see 2 things I really don't care for, maybe 3. Second? Okay, I heard someone say fraction. Okay, I figured that was going to be 1. Next, what did you say? I couldn't hear what you said.
I didn't say that. What you said? I didn't say anything else. I didn't say anything.
Oh, you did. Anyone else besides the fraction? How could we get rid of the fraction? Not by half, by 2. That's a legal move. Multiply the same thing on both sides of the equation by the same number. Hey, that's legal, right? And if I'm going to multiply by 2, guess what I might also choose to multiply by? The negative 2. Because I don't like leading off the equation with a negative sign. It's just my preference. I don't like it. And the other thing I was thinking, I want to write that in descending order of power just because I like it better that way. It's sort of standard form. So can we do all 3 of those at once? Or do we need to do it in 2 or 3 steps? At once? Okay, let's try it. We're going to multiply this whole thing over here by negative 2, but we'll multiply this over here also by negative 2. Okay? And we're going to rearrange the order. So negative 2 times negative 2 would be 4x cubed. See, I went over there and got that one first. Then that would be negative 12x squared, right? And finally, say again? Negative and negative is positive. 2 times 9 halves would be, say again? Okay, 18 halves, which would be 9. That's why we multiply by 2, so we can get rid of that denominator. Remember, that's the whole purpose of it, okay? So that'd be plus 9. X. Don't forget your X. And when you multiply 0 by negative 2, what do you get? 0. Isn't that nice? Okay. Now I have it in a form I like better. There's nothing better about this form. It's just I like it better, okay? And as long as I've made legal moves, you can do that. Now, the main thing to remember is when you multiply by something on the outside, you change every sign on the inside. That became a plus, this became a minus, and that became a plus, okay? Just remember to make, the signs are going to get you most of the time. When something's going to get you, it's those little signs that will sneak up and do it. Sometimes we'll forget to multiply numbers, yeah, but the signs, they're nasty, okay? Now, what would be your next move? Factor, and what do you want to factor first? What you always look for first. Say again?
So what you look for?
Yes. When you're doing factoring. Starts with a C. Say again? Okay. Sometimes, but not necessarily. It's a very common word. Oh, not denominators, common factors. Right? That's what you're doing, factoring. Okay. And do you see any common factors in those three terms? X and X alone. So let's just factor out an X. And what does that leave us with? 4x what? Squared minus 12x plus 9. And that's equal, well, that's not right. My pen's not writing. Equal, and now it's writing 3 times, okay? Equals 0. Okay? You think we're through factoring? No, maybe not. We're kind of hoping not, but otherwise we'd have to use the quadratic formula. And we don't really want to do that right now. Okay. Any idea how we might factor that quadratic? See, once you get it down to a quadratic, factoring's a little bit easier most of the time, or you can use a quadratic formula. What would you try first? Unless any of you happen to see the answer right when you look at it. If not, what would you try? What's the possible factorization of 4x squared? 2x times 2x. Let's try it. Won't hurt. 2x times 2x. And then where do we look next? The sign of the last term, which is plus. What does that tell you about these two signs?
Okay. Plus, ultimately plus.
So it's got to be the same. So you look at the middle sign, and what's it? So that it can't be plus, it better be negative. Negative times negative will give you a plus, right? And then, what's only, not the only, what is one possible factorization for 9?
3.
3 times 3. Let's see if that works. How do we do that? Curses foiled again, right? Okay. 2x times 2x is 4x squared. We knew that was going to work. And what do we do next? The outer 2x times negative 3 is negative 6x. Inner is negative 3 times 2x is negative 6x. And what do those add to? Negative 12x. And then the last plus 9. Yes, that works. Now, do you think you recall why I thought some of you may have seen this at the very beginning? This is called a perfect square trinomial. Remember what the qualifications are for that? The first term needs to be a perfect square. Yes, it is. The last term needs to be a perfect square. Yes, it is. And the middle term has to be twice the product of their square roots. This is a perfect square of 2x. That's a perfect square of 3. And 2x times 3 would be 6x. Double that, 12. So it's got to be 2x minus 3 squared. So, that's equal to 0. What does that tell us? Either product of 3 numbers equals 0, either x equals 0, or 2x minus 3 is equal to 0. I only have to write it once, because it's only going to equal 0 once, right? But you're going to have 2 of them, right? So that's going to give you a multiplicity of 2, because this is 2x minus 3 squared. Okay, so what's going to be our possible 0 then? Solve for x. Say again? That first one's a 0. What about this one? Okay, add 3 to both sides. Okay, that gives us 2x is equal to 3, and then divide by 2. And that gives us x equal 3/2. But it's a double zero because you have one from here and one from there, right? So what does that tell you about what it's going to do to the axis? Not going across, exactly, because it's an even multiplicity. All right, so now we're about ready to graph. So what we do first, let me put some tick marks in here. I'll put a 1, 2, 3, 4, 5, 6, 7, negative 1, 2, 3, 4, 5, 6, positive 1, 2, 3, 4, 5, negative 1, 2, 3, 4. Okay. What 2 points can we plot right now? Zero, 0, and 3/2, 0. 3/2 is between 1 and 2, exactly in the middle. Why will this not? Okay, there we go. So that's 3/2, 0. Because if that's a 0, then it's also the x-intercept is 3/2, 0. Okay, good deal. And we know the end behavior. And we know what happens here at 0. What's it going to do at 0? Cross. So that means that it has to be coming from way up there. So the end behavior is way up there. It can't come from down here because the end behavior is up there. To get this, it would have to cross. So it doesn't. It's going to cross right there. So I can put my cross. It's not going to linger either. It's going to go like this. So this one's heading on up this way. Now I haven't picked my test points yet, so I probably should wait and do that. Okay? But what's it going to do at 3/2, 0? It's going to touch it and then head back down, and sure enough, there's your end behavior. So we already have an idea what this looks like, right? Wow, look at that. Now, they want us to do some test points, so let's do them quickly. What test points would you need to do? I shouldn't have drawn the graph yet, but you have 2 zeros here. So what's some test points? 1, 2, negative 1, okay? Is that the order you want to do them or some other order? Oh, man. I kind of don't want to do that original function, but I guess I better because I monkeyed with it. Okay, so I think we're going to run out of time, right? F of, which one you want to do first? 1. We can do that one. What is it? Add your coefficients. 6 minus 2. Again. 4. Okay. Minus 3.5. No, 4.5. Oh, second. 9/2 is 4.5, isn't it? So 4 minus. Yeah, so that's right. 4 minus 4.5 would be minus 1/2, right? So here at this, we should be minus 1/2. So at x equal 1, we should be minus 1/2 right there. Yeah, I'm not quite at the right place, but I can live with it. But I'll erase this part. I'm going to erase it all. I shouldn't have drawn it. Okay. Oh, I waste too much. Okay. All right, so there we have that point. What's the other point? Test point. -1. So f of -1, I'll just do where I was going right here. That would be a negative 9/2 times -1 plus a 6 times a, oh, look at this. Remember I said I erased too much? I lost my I lost my square here. It disappeared. Okay, so that would be -1 squared, right? Minus 2 times -1 cubed. Why it's not writing, I'm not, there it comes, but it's, okay. Now, okay. Now, Let's evaluate that. What's negative 9/2 times negative 1? Positive 9/2, right? Okay. Plus 6 times what is negative 1 squared? Positive 1. 6 times 1 is 6. And what's negative 1 cubed? So negative 1. And negative 2 times negative 1 is plus 2. Okay. That's gracious. This aggravates me. All right. So this is 8 plus 4.5. That'd be 12.5. Somewhere at negative 1, you're already way off scale. So it's heading up there really steeply. Okay. And then we know it's coming down here, there. Okay. So I think it probably reaches a minimum somewhere here and comes back up here, hangs and goes. But let's do the next one. What is at 2? Alpha of 2. Negative 9/2 times 2 plus 6 times 2 squared is 4. I'm going to speed it along here. Minus 2 times 2 cubed is 8. Okay? So this is going to be negative 9. I like that. And a negative 16. That's okay. And a plus 24. 9 minus 16 is... No, negative 9 minus 16 is negative 25 plus 24 is negative 1. Oh, look at that. At negative 2, you're at negative 1 and heading south all the way. So there's our function, the graph of the function. Heading really fast up here at minus 1. Crosses at 0 because it's a single multiplicity. Okay? Somewhere down here reaches a minimum and goes back up. It shouldn't be pointed like that. It should be rounded. It goes through 1, negative 1/2, 0, negative 3/2, 0 here. Doesn't cross because it's a multiplicity of 2 and goes through 2, 1 and heads south. Stays south. All right. Let me give you a few homework exercises. Okay. And the pictures in the book, I don't know if it's accurate. We'll start next time with intermediate value theorem. Okay? And homework exercises here will be any of the odds. I do all of 9 through 14. The odds are in the back and at calcchat.com. Do any of the odds 15 or 17. Both are at CalcChat. 17's at CalcView. Do any of the odds 19 to 27, they're all at CalcChat, 21's at CalcView. Do either 29 or 31, they're both at CalcChat. And do any of the odds 33 to 47, they're all at CalcChat, 43's at CalcView. And then there's using technology, I'll let you decide whether you're going to do that, 49 or 51, they're both at CalcChat. And then stop there, we'll pick up the rest of those next time.
When do we have our next quiz?
When we finish 2.3, so it'll be very soon, probably Tuesday or Thursday when we get back. And there's one other assignment. Have a good spring break. You have to now. If you don't, I'm going to mark you out. Down. Yeah, we're going over to Georgia, where I grew up.
Okay, have fun.
I will try. Thank you.
I have a question.
Sure.
You're my advisor.
Oh, poor thing.
I know.
My condolences.
I need to set up a time to meet with you after spring break. Then we set up.
Okay.